We didn't start recording?
No, it just stopped a little while ago, like 2 minutes, 3 minutes ago, I think. Now it started again. Thank you.
Okay. So we will see 2 videos in this case?
Yes, I think so.
طيب اما نشوف ان شاء الله. Okay. Let us explain why A is a stable equilibrium point in view of the swing equation. If B mechanical is greater than B electrical, system will accelerate or decelerate?
Accelerate.
Accelerate means what? And the speed
increase.
And the delta increases. Right?
Yes.
طيب, if B mechanical, let them be electrical. So we have deceleration, omega decrease, the angle also decrease. طيب, okay, let us assume that we have disturbance at point A, small disturbance at point A. If, for example, B electrical reduces, and we have B electrical here. طبعا B electrical is one point of the curve. B electrical is one point of the curve. If B electrical goes below at this point, and what will happen? B electrical becomes lower than B mechanical. مظبوط؟ يعني if we reduce the load, for example, if we reduce the load, the machine is operating here. We reduce the load. So the voltage, the load becomes here. B electrical is lower than the value at point A. Okay? So in this case, B mechanical is higher than B electrical. What will happen? B mechanical greater than B electrical, the machine will accelerate and the angle will increase. So the machine will accelerate and the angle will increase. So the machine will go back to this point. And vice versa. Also, the B electrical becomes higher than this point. What will happen? B electrical at this point becomes higher than B mechanical. So the machine will decelerate and the angle will decrease until it goes back to this point. So with any disturbance, a small disturbance around A, the machine will be back to its original state. Is it clear?
Yes, doctor.
So point A is called stable equilibrium point, SEB. This is unstable equilibrium point. Why? Assume that the electrical power decreases. We are here. What will happen? B mechanical now greater than B electrical. So what will happen? The delta will increase. So we will not go back to B, but we will go in this direction of delta increase. So we are going further from the equilibrium point, P. So with any disturbance around B, the system becomes unstable. So in this case, we say the point B is unstable equilibrium point. Is it clear? So A and B are equilibrium points. Let us consider a slight variation about the equilibrium points. For point A, if theta is greater than theta 1, or theta less than theta 1, if you are here or here, at any point here or here, so the system will be back at point A. The machine will slow down or speed up to restore the angle theta. Point A is a stable equilibrium point. And the opposite for B, as we mentioned, if theta is greater than theta 2, if the electrical power is lower than the normal due to reduction of the load or something of this, B mechanical is greater and the machine will speed up and the angle will increase. So going far from the synchronous operation cannot be maintained. It will not come back to the equilibrium point. The machine loses synchronism or pulls out of step, becomes out of step. So point B is called unstable equilibrium point. So in this case, what is the stability criteria? The operating point theta should be less than or equal 90 degrees. This is the stability criteria for single machine infinite bus system. Okay, so you can operate the single machine infinite bus system at any point of this curve up to 90 degrees. So this is the stability criteria. So let us assume that if we have two machines, synchronous generator and synchronous motor.
Doctor, can you allow one question, please?
Yes, please, go ahead.
Doctor, for the point B in the previous slide, for the point B, it's unstable equilibrium point from one direction or both direction. So in case the load increase, the BE will more than BM, so delta will reduce. So it will get back to point A, or this is not right?
You want to move in this direction. Again, if we have here any disturbance, and the B electrical becomes greater than B mechanical.
So delta will reduce.
What will happen?
Delta will reduce.
Delta will reduce. Yes.
So
but definitely, it will not reduce. It will not go all the way here. The B electrical here is greater than B mechanical. So we have deceleration. So this deceleration means the speed will be what? Will be lower, and the angle will be lower. Yes, we will move here, but are you going to keep the speed going down and down? And if you move if you want to move this, B electrical becomes here now. So that means the reduction in speed is very huge. If B electrical becomes here and this is B mechanical, so the reduction of the frequency will be higher and higher. And this is not acceptable. Did you get the point?
Yes, so at least we can say point B is stable in one direction. So in case load increased, so it's stable, but if load reduced, it will lead to instability.
But for how much the load can increase. انك انت محدد برضه بالسبيد والفريكونسي.
Okay, right. Yes, you're
You
right.
cannot يعني say انه okay, let us increase the power for to this point مثلا. So in this case, you have here the deceleration, and the speed will be, or the frequency will be lower and lower. And maybe
major drop.
59 or 58 hertz, and this is not acceptable. You cannot work as such. Is it clear?
Yeah, it's clear. So point B is unworkable point at all.
At all.
Yeah, right.
At all. يعني هي equilibrium point. يعني in terms of B mechanical and B electrical, they are equal. But with any disturbance, any small disturbance, the system will be unstable. So this is like مثلا, for example, if you have as such, this point it's exactly the same. This point is a stable equilibrium point. If you have any ball, okay, this ball will, go back and forth until it will again reach here. If you put it here, if you put it here, so it will come back to this point, right? But if this point is an equilibrium point, but with any disturbance, with any oscillation here, this is unstable equilibrium point. So if the ball is here, and with any movement, whether this way or that way, so it will become unstable. Is it clear?
Yes, right.
Okay.
So, Doctor, the B maximum at 90 degree is also not right. So we don't have B maximum at 90 because after 90 it will lead to unstable.
Yes. Well, this is the maximum, and you cannot go beyond this. If this is the maximum BE maximum, this will happen at 90 degrees. Is it clear? Okay, for two machines connected together, you have here machine number 1 and machine number 2. This is the angle delta 1, delta 2, and machine reactance. And this is machine 2 reactance, and this is the transmission line in between. So with this system, what you can do, you can see what do you think the stability criteria here? What do you think? The first case for single machine infinite bus, delta should be less than or equal 90 degrees. Okay, so this is the stability criteria for single machine infinite bus. What do you think here? What do you think for two machines? Any suggestion, Ayub?
I think, Doctor, the difference between delta 2 minus delta 1 should be less than 90 degree.
Okay. Angle difference delta 1 minus delta 2 should be lower than or equal 90 degrees. You are right. What we can do to derive this or to develop this criteria is to write the swing equation for machine number 1 and the swing equation for machine number 2. And then we can get one, of course, if this is B electrical 1, where this power will go to the machine number 2. So this is BE1, which is equal to minus, this is BE2, and this is BE1. So BE1 equal to minus BE2. And the mechanical power here, which is equal to BE1, B mechanical 1, and this is B mechanical 2, will also be equal and opposite. And in this case, you can write the the swing equation of machine number 1 and the machine number 2 and go forward. So theta is defined as delta 1 minus delta 2, angle difference, and then theta double dot equal to this. This is will be used now. Delta 1 dot double dot, which is the swing equation of the machine number 1, equal to omega s over 2h1 and B mechanical 1 minus B mechanical electrical 1. For the machine number 2, we can write the same swing equation. You have here H2, B mechanical 2, and B electrical 2. Of course, you can get the difference, delta 1 double dot minus delta 2 double dot, which is theta double dot. And you can say B mechanical 1, you have the difference. So B mechanical 1 with B mechanical 2 will be equal to minus B mechanical 1, and this is equal to minus B electrical 1. So you can have this term will be equal to that term, okay? And then you can, by taking the difference, you can take this term as a common factor, and then you will end up with omega s over 2 also as a common factor. So you have 1 over h1 and 1 over h2. So that means you have a swing equation. You can replace the two swing equation by one swing equation where h is the difference. The inertia of the equivalent machine is a function of the inertia of the machine number 1 and the inertia of machine number 2. So for two machine system, BE1 equal to minus BE2, let us call it BE. B mechanical 1 equal to minus B mechanical 2 equal to BM. So delta 1, 2 equal to delta 1 minus delta 2. So when we take the difference here, so this delta double dot equal to B mechanical minus B electrical. As I mentioned, and if you replace this by BM and this is by BE, and here is minus BM, and this is plus BE, so this becomes plus BE. So you take here minus as a common factor, so it becomes BM minus BE, and you have here BM minus BE, so you can take it as a common factor here. So you have BM minus BE as a common factor, BM minus BE, and you have omega s over 2, and this is H equivalent. This H equivalent is a function of H1 and H2. So you have 1 H1 over, as if these machines are running in parallel, and you have H inertia for machine number 1 and the machine number 2. So two inertia in parallel, you have 1 over H equivalent or 1 over R equivalent equal to 1 over R1 plus 1 over R2. The same law can be implemented here for the inertia for 1 over H equivalent equal to this, or H equivalent equal to H1, H2 over H1 plus H2. And here mathematically you can replace this system by a single machine. The equivalent or inertia of that machine is the H equivalent, which is 1 over H1 plus 1 over H2. So the stability is governed by the how one machine pulls apart delta 1 minus delta 2 from each other. Okay. So what governs the stability here is delta 1 minus delta 2. Difference between delta 1 and delta 2. For multi-machine, here you have, of course, several machines in your system. So in this case, you can write the swing equation of each machine. This is machine number 1 or machine number I, 2HI delta I double dot equal to B mechanical minus B electrical. This angle, what is the difference? What is the reference of this angle? This angle is measured with respect to synchronous reference. And you have to have a reference in this system. If you have multi-machine system, you have to define this reference could be one machine, similar to what we are doing in load flow studies. We consider مثلا the slack bus as our reference, is angle 0, and we relate all the angles to that reference. So this is one option. The second option, or the second way here, is to define what we call center of angle. Center of angle. And we can define a fictitious reference, which is, you find the weighted angles with respect to the inertia, and then you define this as your reference, and you relate all the angles to that one. You have to have a reference anyway. So you have to have a reference in this case, and this reference could be either one machine, you consider its angle as 0, or you define the center of angle, as we will define in next slide maybe, or something. We will define it here now. To examine the stability, we need a reference to observe the pulling apart of the machines. So make the angle of the largest machine in the system the reference angle, and you can have the angle with respect to the largest machine. So this is one option. The second option is to define a center of angle, like a center of gravity or whatever, similar approach. Center of angle equal to summation of all angles over the number of machines. So you have the average of all the angles. Okay. So in this case, you can define the angle of all machines at the center of angle of all machines, and the plot delta I versus center of angle of all machines. I don't know whether anybody carried out before some stability studies on ETAB or something like this. Do we have any of you carry out transient stability studies in ETAB?
Yes, doctor.
Who? Omar?
Yes.
So what do you experience regarding the angle? If you plot the angle deltas versus the time?
In terms of curves.
So let me ask you, if you run the transient stability in ETAB, for example, and you found the angles of machine number 1, machine number 2, machine number 3, 4, 5, and so on, as follows.
Okay.
What do you think? If you want to judge whether the system is stable or unstable, and these are the angles versus the time.
Okay.
System is stable or unstable?
The system is partially stable.
يعني ايه partially يا مان؟ why partially؟ يعني you want to hold the stick from the middle or what?
Not system defense, doctor. The curves are not equal, but like almost parallel.
System here is stable. Yes, you're right. System here is stable. The angle difference here, what we are interested in, the angle difference. Are the angle difference increases or decreases? If you draw the center of angle, this is the center of angle versus time. Center of angle is defined as the angle at each instant, summation over the number of machines. So this is the center of angle. Okay, so in this case, you can see the angles are going around the center of angle. The angle difference decreases, right? So the system becomes stable. The system is stable. This curve is similar to this curve. When you see these curves, the system is stable or unstable? This one.
Stable.
System is stable طبعا. And from this swing curve delta versus t, we can say the system is stable. Angles are, decreasing. We have damping with time. And the oscillation, the overshot. If this is the overshot deviation of the angle, so this deviation is decreasing with time. So system is stable. This system also is stable. But here we defined here the center of angle. This we compare the angles of a certain machine with this center of angle. And this center of angle is summation with respect to time here. So in this case, you have this is center of angle. Okay, so you can have either way to define the reference for the multi-machine. Either you take the largest machine as your reference. This is similar to what we are doing in load flow, or you define a center of angle as such. So you do when you solve the swing equation, you have delta 1 of I of time t مثلا, and delta 2 of time t at a certain time t0, T0 delta 3 of T0 and so on. So you get center of angle, you add all them up and you divide by the number of machine, so you get the center of angle, and then you can redefine delta 1 of T0 equal to delta 1 of T0 minus center of angle. And you define this as you subtract all these, the center of angle from all these angles. Okay. Okay, any question? We have Abdulaziz Khalid, please. You have a question?
Yes, Doctor. In the first graph, why are we saying the system will be stable even though the angle is increasing over time?
The angle is increasing, but the difference is not increasing. The angle is increasing, but the difference between the angles is not increasing. Am I right?
Yes, but isn't the angle difference between the rotational or mechanical rotation to the reference of this? What I understand is that the machine is always accelerating.
لا, يعني you have here, this is your reference. This is your reference. Assume that this is the machine number 1 and this is the machine number 2. Hatta even if these machines are running, but they are running together. They are going far from the reference, right? But the difference between them is kept almost the same. So the machines are still in synchronism. They are very tight with each other. Okay? So similar to what we have in load flow, we are not interested in the absolute value of the angle, but we are interested in the difference between the angles. This is why in load flow we define the slack bus as our reference, and we relate all the angles to that reference. Okay, so we are interested here in stability also. We are interested in the angle difference, delta 1 minus delta 2. And we need delta 1, and for the last example or last configuration, which is the 2-machine system, we are interested in delta 1 minus delta 2. We are interested in the angle difference. This could be higher than 90, and this could be also higher than 90. But this is the reference with respect to the reference. Okay, so this reference is just you can take any phasor as your reference. But what we are important here, what is important here is the angle difference. So this is why for this configuration system is stable. When you look at this, yes, the angles are increasing with time, but the angle difference is decreasing. The angle difference is decreasing. Okay? Is it clear?
Thank you, Doctor. Yes, thanks.
Any question? Unfortunately, time is over.
Okay.
Mm-hmm.
Yeah, I just want to ask the relationship between these angles, maybe the reference angle, compare to the swing bus and the slack bus in the power system.
Yes, here. You can take the largest machine as your reference. So you need the angle difference here. What we are interested in is the angle difference. The angle difference means the machines are coherent. The machines are coherent. They are tied to each other. So they are still in synchronism. They are running together. Okay? So the system is stable here.
Thank you.
Power angle, and I think we have to stop here. We didn't pray Maghrib yet. Let us stop here and continue next class, inshallah, with the bar angle. Any question? Muhammad sir, yes, please.
Doctor, the difference between the angles still should be less or equal to 90 degree?
Yes. Yes. The angle difference. You are interested in the angle difference. How much the angle difference? Similar to what we have in the two machine system, delta 1 minus delta 2 should be less than 90 degrees for stability. Also here, if you take the maximum angle and the minimum angle of the machines here, assume that this is the maximum and this is the minimum, and you see the angle difference here. How much is this angle? Is it greater than 90 or less than 90? This will also govern the stability of the system, the angle difference. Okay?
Okay, thank you.
Any other question? If this is the case, so we can end our class and see you on Wednesday, inshallah.
Thank you, Doctor.
Okay, thanks.
Thank you.
Assalam.